Hello everyone, and welcome to the tutorial on practical mechanism design for bidders with bounded rationality, which will be presented by myself, Vasilis Gkatzelis, and Daniel Schoepflin, who up until this term is still a PhD student at Drexel, but will soon be transitioning into a postdoc at MSRI at Berkeley and then Rutgers. So before we jump into any details, let me start off and provide the overall outline of the tutorial. So I'm first going to start off and talk about a classic family of mechanism design problems, specifically binary single parameter problems that are going to be the main focus of this tutorial. And then Dan will follow up and discuss bounded rationality in the context of auctions, and specifically focusing on obvious strategy proof as one of the exciting recent definitions in this area when it comes to dealing with boundedly rational bidders. After that, the rest of the talk will focus on clock auctions, which are a very powerful tool for designing practical auctions that do not require a lot from the bidders. They have low entry bar, and they provide strong incentive guarantees, trust guarantees, privacy guarantees, and so on. We'll discuss these guarantees during the tutorial. And then I will first focus on what can be achieved using clock auctions without priors, that is, clock auctions that have no prior information regarding the values of the bidders, and both deterministic and randomized, and what can be achieved, what are positive and negative results there, and what are interesting open problems. Then we'll take a 45-minute break, and then Dan, in the second half of the tutorial, will focus on Bayesian clock auctions, so in other words, clock auctions with prior information, and how to use this prior information. And also budget feasible clock auctions, which are reverse auctions now instead of forward auctions. Finally, toward the end, Dan will wrap up by even extending further beyond single parameter settings into multi-parameter settings and discussing what can be done with clock auctions. So I would say most of the open problems will come from the clock auctions portions of the talk. And I want to mention that if anyone in the audience is not necessarily particularly interested in bounded rationality modeling and kind of issues that arise there, but really want some compelling and well-motivated open problems, they can move directly forward to the clock auction aspect of this tutorial, where we try to explicitly provide concrete problems, some of which we think are really fundamental, because clock auctions are really well-motivated and important family of auctions that we do not really understand well enough in terms of, for instance, how to use randomization to get improved guarantees and what is the best achievable guarantee, or how to use prior information to guide these auctions and what can be achieved with this additional information. So many interesting problems. We'll try to emphasize which ones we think are the most exciting ones. So yeah, let me just jump in directly into the definition of this single parameter binary auction environment that we're going to be mostly focusing on. And you want to envision a designer who's offering a service and is trying to design an auction to sell that service to a set of bidders, each of which has a private value. Each bidder I has a private value VI for being served. That's their willingness to pay, how much they're willing to pay for this service. And there's also a feasibility constraint that might restrict what subsets of bidders can be simultaneously served, can be provided this service at the same time. So for instance, just to provide a visual example, imagine we have these 12 bidders, and for each one has a private value. Again, this information, the value under each bidder, is known only to that bidder. And there's some feasibility constraint that doesn't allow us to just serve, potentially doesn't allow us to serve everyone. For instance, maybe that's one way to visualize it. Each rectangle corresponds to a feasible set. So for instance, everyone in the blue set can be served simultaneously, but you cannot in general serve people unless they all belong under one rectangle altogether. So you cannot mix and match across different rectangles unless there's a bigger different rectangle that contains all the bidders you're trying to serve. And the goal throughout the talk will be to maximize social welfare. Specifically, we're going to try to serve a feasible subset, so try to find who to serve, aiming to maximize the total value. In other words, maximize the sum of the values of the bidders that we're actually serving. So trying to make have the biggest impact with the server, give it to the people that will value it the most. And just instantiated here in the example in the bottom right, here that would be the blue set. If you actually go through each one of these feasible sets, each one of these colored rectangles, and try to add up the values of the bidders inside them. You'll verify that blue is the one with the highest value because it has 5 plus 5 plus 3 plus 2. It adds up to 15, which is the largest social welfare. So to give some examples, this environment, the single parameter binary environment, captures many well-motivated problems. And the main way in which they differ is usually based on the feasibility constraint that's provided. That feasibility constraint can be implied by different scarcity constraints. So just to see one example, this environment captures spectrum auctions, where the FCC, for instance, would be the designer and is trying to sell the license for using some particular frequency to a set of bidders who would be the broadcasters. They're trying to buy that license so they can broadcast over that frequency. But the issue then, the feasibility constraint, is that maybe two broadcasters that are close by might not be able to use the same frequency because there's too close and there's going to be a conflict. And this kind of feasibility constraint could be potentially captured by a conflict graph that essentially says two neighbors in this graph, as we see the red edges here, cannot be assigned the same frequency. So that is because that would lead to a conflict. Another example that's very natural is, for instance, selling tickets for seats in a flight. In this case, the feasibility constraint corresponds to a knapsack constraint. In the previous one, it was an independent set, maximum weight independent set. This is a knapsack feasibility constraint. So imagine we have some limited, let's say 6 seats available on the plane. We're trying to sell them to a set of different bidders. Now, the bidders each bidder represents a family, let's say a family of 4 or a family of 3. And we cannot serve them all. If we have, let's say, 6 seats, we cannot just serve them all because there's not enough seats to go around. And in that case, again, we would try to figure out who we should be serving, try to maximize the value. And again, we're focusing on value. There's connection to revenue, but we're mostly going to be focused, and that are discussed in some of these papers that we point to. But throughout the tutorial, we're going to be focusing on maximizing social welfare. And what unifies these different problems, depending on what feasibility constraint one chooses, is one of the main obstacles here is the fact that if we want to optimize social welfare, well, we need to elicit some kind of information regarding the bidder's true values. If we don't know anything about their true values, there's no way for us to choose even a feasible set that approximately maximizes social welfare. So we need to somehow extract this information. And the tricky part about this is that this introduces room for manipulation. So we depend on the bidders themselves, because they are the only ones who know this information, to share a portion or all of that information with us. And that means that we depend on them and they can try to manipulate the auction to their advantage. And therefore, this gives rise to the second obstacle, which is we need to elicit this information, gather information regarding the bidder's values in a way that does not introduce room for manipulation. And this is at the core of game theory, of mechanism design specifically. And there's many auctions, the notion, for instance, of strategy proofness or truthfulness, which ensures provably that it's a dominant strategy for someone to, let's say, report their true value directly to the auctioneer. However, in this tutorial, we're going to be digging a little bit deeper, and we're not going to be, this notion of strategy proofness wouldn't suffice, because as it turns out, if people are not fully rational, even if they're facing an auction that's strategy proof, oftentimes they might still not be able to identify what their optimal strategy is, i.e. truthfully reporting the value, might still try to manipulate it. And even if they weren't eventually able to identify it, that might require effort on their end. And our goal throughout this tutorial is to design practical mechanisms that require as little as possible from the bidders, and trying to understand the extent to which we can do that without losing that much in terms of efficiency, in terms of social welfare. And from this point onward, Dan will first talk about bounded rationality and motivate some of this additional kind of strengthening of incentives. But even beyond these incentives, the clock auctions that are the main device we're going to be focusing on provide, as I mentioned before, privacy and trust guarantees beyond their incentive guarantees that make them very practical. And most of the tutorial is going to be focusing on what can be done if we restrict ourselves to using clock auctions.
As Vasilis mentioned, we're going to be thinking about clock auctions in a variety of settings. But before we move on to these more general settings, let's think about a much simpler mechanism design problem, and likely one of the first kinds of questions you may teach or face in an introductory course on mechanism design. Suppose you're an auctioneer and you're looking to allocate a new phone to one of several buyers, each with a private value for receiving the phone. You want to allocate the phone to the bidder with the highest private value, but need to somehow acquire the private information from the bidders in a way such that they don't misreport their values. In other words, we want a strategy-proof and social welfare maximizing auction. And as such, you run a sealed bid second price auction and have the bidders report their private values directly to you. You serve the highest bidder, green, at a price equal to the second highest bid, 550, which is the bid of the blue bidder. And lucky for us, the second price auction is strategy-proof and social welfare maximizing. So we've achieved our goal. And you can actually show these two facts with only a couple lines of proof. But unfortunately, despite the simplicity, there's a gap here between theory and practice, since unfortunately it's long been observed in laboratory experiments that unsophisticated bidders don't follow their truthful strategy in a second price auction. In other words, they report something different from their true private values. Moreover, this non-truthful, non-optimal bidding may persist even as bidders participate and are supposedly learning how to bid in auctions. And our setting here is remarkably simple, and yet is still poorly modeled by the classical theory of mechanism design. So perhaps what we may think is simple turns out to be more complicated than we imagined. And as it turns out, the agents that our mechanisms encounter in the wild seem to be far from the traditional, perfectly rational Homo economicus that a great deal of the mechanism design literature assumes, and which the results sometimes rely upon. In fact, agents deviating from their optimal strategy has been observed in many classic mechanism design settings. And while the focus of our tutorial here is going to be on auctions, suboptimal, non-truthful behavior has been observed in school choice, voting, and two-sided matching settings, just to name a few. So as such, there's a growing literature which aims to characterize strategic misbehaviors or failures in reasoning and justify why they may occur. And we want to do this so we can develop a theory which better models agents observed in the real world and design mechanisms better for such agents. And the central questions we're going to be concerned with in this first part are, what are the possible causes of bidder misbehavior, and how can we design mechanisms which are more robust to bounded rationality? Many possible reasons have been proposed in the literature for agent misbehavior in a variety of games, like the sealed bid second price auction. And one sort of major line of literature assumes that agents understand the functionality of the game and understand how the game operates, but misapprehend opponent strategies or have mistaken beliefs about them. There's a wide variety of literature on this. Just to name a few: cursed equilibrium, which is related to the winner's curse and loser's curse, cognitive hierarchy and level K equilibria, and analogy-based equilibria have all been proposed to sort of model this universe. But problematically, none of these concepts speak to the agent misbehavior in the second price auction, because truthfulness is a dominant strategy in the second price auction. It's always a best response to report your true bid to the auctioneer. You don't need to believe anything about what your opponents are doing. So an alternative explanation that gets a little bit closer to maybe the problems we have in the second price auction suggests that agents may not actually understand the game due to its form. And because they misunderstand the game, they make errors in contingent reasoning. To get a better sense of what we might mean by contingent reasoning failure, let's take another look at the second price auction and imagine ourselves in the position of the orange bidder. Since we're running a sealed bid auction, the orange bidder doesn't have access to the private value or the bid of the blue bidder. And if we consider the game tree of the second price auction and try to reconstruct a possible mistake in contingent reasoning, we can imagine the start of the game as the blue bidder being called to bid, and the possible action branches in the tree as all the possible bids that she could submit. When the orange bidder is called to bid, all of the possible states of the world are in the same information set, since orange hasn't learned anything. Thus, on one possible branch, the true branch, where blue bids 550 and orange bids truthfully, orange can observe that she obtains no utility. On the false branch, where blue bids 300 and orange misreports and bids 600, orange obtains positive utility. But when orange is called to act, both of these nodes, blue bids 300 and blue bids 550, are in the current information set. So from orange's perspective, there are current states of the world where bidding truthfully is worse than bidding non-truthfully. So a very plausible explanation for Orange possibly misreporting her value is that she doesn't reason correctly about all of the contingencies that arise from true and false bidding. Because the key point that Orange overlooks, that's a key in the proof of the truthfulness of the second price auction, is that bidding modestly in excess of her private value only increases her chance of winning compared to her true bid in cases where she wouldn't want to win. But unfortunately, as Kegel et al. Eloquently point out, this fact is far from obvious under the sealed bid procedure. So since contingent reasoning seems to be difficult, even in a really simple single item setting, perhaps we need to re-examine the design of auctions and other mechanisms to figure out alternatives that makes optimal truth-telling strategies much more apparent. Enter the English auction, which many have argued is actually a simple mechanism. We have our same setup as before, where an auctioneer aims to allocate a cell phone to one bidder with the highest private value, but instead of requesting bidders report their values directly to the auctioneer, instead the auctioneer asks a series of yes or no questions to the bidders. In this case, let's say, starting by asking Blue if she's willing to pay $100. Blue then compares the ask to her private value and responds either yes or no. A yes means she stays in, and if she wins, she's going to pay at least $100, and a no means that she exits permanently, winning nothing. After Blue responds, the auctioneer just moves down the line, approaching the next bidder, observing responses, and so on and so forth, gradually raising the asking prices for each bidder until finally a bidder is asked a price which is too high. And to which this case, since Yellow is asked a bid of 401, asked if she would be willing to pay 401 and her private value is 400, she responds no, and she permanently exits the auction. And this just continues until all but one bidder has exited the auction, at which point the auction terminates and the last remaining bidder receives the phone at the most recently accepted price. And this auction form, I claim, is simpler than the sealed bid, second price sealed bid auction. And this claim has been backed up by empirical evidence. Since in laboratory experiments, it's been observed that bidders are far more likely to act optimally, in other words, truthfully, when facing an English auction. And this is maybe particularly surprising, given that the English auction and the second price auction implements the same outcome and have the same normal form. On the other hand, despite the striking similarity between the normal forms and outcomes of the two auctions, the extensive form and contingent reasoning required are radically different. To see this in action, let's imagine again Orange's decision-making process when she's called to act. If we think about what happens when Orange is called, say, after Blue has said she's willing to pay $100, Orange, rather than distinguishing between all of her possible types by reporting her bid, she only needs to distinguish between her lowest remaining type, say values less than 101, and her other possible types, values 101 and above. It is now easy for her to verify that if she misreports, she'll always obtain utility 0, since she exits the auction, but if she remains in the auction, she will obtain no less than 0 utility in the worst case. The auctioneer asks Orange a price, and if she refuses the offer, she can easily observe that she won't win the item. Whereas if she stays in, she might win the item. So staying in seems obviously better than exiting at the current price level. And the solution concept known as obvious strategy proofness, originally proposed in an influential paper by Shengwu Li, exactly captures and formalizes this intuitive notion of strategic simplicity. Li defines a strategy S sub I of player I as obviously dominant in an extensive form game if for any deviating strategy S prime I, conditioned on the first point in the game where the two strategies yield different actions, the worst case utility obtained by following Si is weakly better than the best case utility obtained by following S prime I. Then a mechanism is obviously strategy proof if following the truth-telling strategy is obviously dominant. Then based on this definition, if we look at the two game trees for the second price sealed bid auction and the English auction, we can see that the second price sealed bid auction is not OSP, whereas the English auction is OSP. And because these two mechanisms implement the same outcome, we may observe that whether or not a mechanism is obviously strategy proof depends on its implementation. So we don't have a direct revelation principle for OSP mechanisms, really. And this is, I think, a straightforward observation after the fact, but I think a really interesting observation nonetheless. It raises a lot of deep theoretical and technical questions about how one needs to actually design the implementation of mechanisms if we want them to be OSP. And there's a fairly substantial line of literature examining the design of OSP mechanisms in a variety of settings, and in parallel, a line of work investigating when our classically taught mechanisms, like the second price auction, are or are not OSP. For example, there's been work on one-sided and two-sided matching, strategic voting, scheduling, and facility location, just to name a few. But for the auction settings we're looking at in this tutorial, Lee provides a compelling, straightforward characterization. In single parameter binary allocation problems, the class of OSP mechanisms are those where bidders face monotonically ascending prices or monotonically descending payment offers. And this characterization then immediately shows that the English auction is OSP, whereas the second price auction is not. However, in this simple setting, it appears that we can achieve OSP with no loss to the social welfare. But you can probably imagine that as we move to more complex settings, designing OSP auctions may require a more careful approach and may necessarily lose us something. So for the remainder of the tutorial, we want to sort of begin to investigate this fundamental question about how we should design OSP auctions in more general single parameter binary auction settings, and when we must or must not lose social welfare. But to see an example of a more general setting, let's revisit the example Vasilis mentioned earlier about an auctioneer looking to allocate the final seats on a nearly full flight. A set of families all have different sizes and private values, denoting their value for boarding the flight. And we want to maximize the social welfare, which is the sum of the values of the families we serve. Like in this particular case, if we serve blue and green, we would obtain a social welfare of 1,050. So in other words, we have this knapsack feasibility constraint over the families that we can serve. Let's say there's 6 seats remaining on the plane, then the maximal feasible sets in this knapsack constraint are gray, yellow, and blue, green and blue, and green and gray. And of course, this feasibility constraint is downward closed, so we can serve any subset of these maximal sets. Since we need to elicit the private values from the families in order to determine who we want to serve, we can, of course, run a sealed bid auction and ask the families to report their values as bids directly to the auctioneer. But as we saw before with the second price auction, sealed bid auctions have issues related to incentives. They're not OSP, but they also have issues related to trust, since even if bidders are fully rational, they have to trust that the auctioneer is not going to mishandle their private value information and is going to compute prices correctly. Moreover, there are issues related to privacy, since bidders have to report their private value information directly to the auctioneer. This could be problematic if a bidder has unusually high value, for example, since the auctioneer may be able to use this information against them in the future. So rather than a sealed bid auction, we'd like something more analogous to the English auction, but for more general settings. And Milgram and Segal proposed a natural generalization of the English auction, which they call clock auctions. In a clock auction, rather than report the bid value directly to the auctioneer, bidders face a clock price, which represents their current asking price. These clock prices monotonically increase and may do so uniformly, but need not, since clock prices are a price for being served, not an item price, not a price per ticket in this example. But prices will continue to rise until at some point, like in the English auction, a bidder is faced with a price which is too high, at which point they can reject the price and permanently exit the auction. And this process will continue, causing bidders to exit until we finally arrive at a feasible subset of bidders who are served at their most recently accepted clock price. So clock auctions have a form that's more analogous to the English auction, which means hopefully it's going to get better properties. And immediately you may be saying, oh, based on Lee's characterization, it must be that clock auctions are obviously strategy proof. But in fact, they resolve more issues with the sealed bid format that I mentioned before. They have numerous appealing practical and theoretical properties that make them more reasonable than sealed bid auctions in many practical settings. We get our better incentives, we get obvious strategy proofness, which in turn implies weak group strategy proofness. But also, clock auctions don't require that the bidders trust that the auctioneer is performing pricing computations correctly, because they can see the pricing happening before them, right? It's completely transparent what they're going to be charged. And finally, clock auctions also help with privacy by offering winners at least, unconditional winner privacy, which Milgram and Segal define in their paper proposing clock auctions. And unconditional winner privacy loosely means that winning bidders only reveal that their private value is above the threshold bid. So bidders never actually, if they're winners, communicate their true value to the auctioneer. And what you can show is that if you want these properties, much like with Lee's characterization, if you want unconditional winner privacy, you need to design a clock auction. So if you agree, like I do, that these are all reasonable properties that are particularly practical, you have to design a clock auction. Which raises the question that we'll sort of tackle in the remaining part of the tutorial, which is clock auctions are inherently more restrictive than sealed bid mechanisms. And it allows them, the implementation of clock auctions allows them to have these stronger, more desirable properties. So does this restrictiveness actually come at a cost? And that's what we'll explore as we move forward.
Okay, so now let's jump into more formally defining the setting that we're going to be dealing with in order to provide some more technical results regarding the performance of clock auctions. So we're going to be facing a set N of N bidders. And as I mentioned before, each bidder I in N has a private value VI for receiving the service that's being offered. And the social welfare of a set S is the sum, which we denote by V of S, is the sum of the values of the bidders in that set. That's a feasible, for instance, for a feasible set of bidders, that's the sum of the values. And we're going to have a feasibility constraint that we're going to essentially model by saying F, calligraphic F, is the collection of all feasible subsets. And throughout the talk, we're going to be making this mild, very natural assumption that feasibility constraint is downward closed, meaning if a set is feasible, then every subset of that set is feasible. If you can serve a specific set of people, then you can serve any subset of those people as well. And therefore, once you have downward closed feasibility constraint, you can also uniquely define the constraint by its maximal feasible sets. So we're going to be using K to denote the number of such maximal feasible sets. That is a set, a feasible set where if you add any one more bidder to it, it's going to become infeasible. And we're going to be using O to capture the social welfare maximizing subset and opt for the social welfare of opt, in other words, the sum of the values of the bidders in the optimal subset, feasible subset. And our goal, the way we're going to be evaluating the performance of clock auctions, is using a worst case approximation guarantee. Specifically, we'll say an auction achieves an alpha approximation if it serves a set S such that the social welfare of S is at least an alpha fraction of the optimal social welfare. And also, just as a final piece of notation, we're going to be using PI to denote the payment of bidder I, and the revenue of a set as rev of S is going to be just the sum of the prices. Given a set of bidders, we sum up their prices. That gives us the revenue for that set if we were to kind of serve these people and get the payment. So given this formal setting, I want to emphasize, and that's important, it's throughout the rest of the tutorial, that we actually focus on information limitations of these clock auctions, not on computational ones. Many of these problems, these binary single parameter problems, are computationally intractable or computationally demanding anyways. Our main goal is to see the extent to which information limitations that are imposed by clock auctions add to add an overhead, so that these information limitations cause inapproximability. So throughout, we're going to be assuming we have a black box algorithm that solves some optimization problems, like finding the optimal feasible set given some information, or an approximation for that. Many of our results just plug and play or work for an approximation algorithm. But I want to emphasize that the focus is on information limitations that are already quite significant in some cases. So let me, in one slide, provide an overview of the results that we're going to be discussing here for the first part of the tutorial. And they're all focusing on prior free clock auctions. In other words, clock auctions that have no prior information regarding the values of the participants, the VIs. They have no information regarding the VIs. And we're going to be discussing first a negative result and then two positive ones. And let me take some time here to discuss and motivate what we take out of each one of those, why these are part of the tutorial, and then we'll discuss exactly what each one contributes and what are the open problems that remain. So the first one is a negative result. That's one of the early results in this literature that actually showed somewhat of a pessimistic statement regarding the performance of clock auctions. Specifically, it focused on an instance with a very simple feasibility constraint, just two maximal feasible sets. We'll see that in detail soon. And it showed that if the mechanism, the clock auction, has to be deterministic and it has no prior information, that even for that very simple feasibility constraint, for that very simple instance, it cannot achieve better than a logarithmic approximation of social welfare. So that was one of the first results in this literature on trying to evaluate the performance of clock auctions. And given the simplicity of the instance for which this negative result was exhibited, one could assume that maybe for more general downward closed feasibility constraints, the negative news would be even worse. It led to a pause of kind of results for a few years. But this positive result that we're going to discuss next provides us with an insight regarding what one can do using clock auctions. And in fact, this positive result, which is more recent, provides a deterministic prior free clock auction that actually matches that same bound, the logarithmic bound, for any downward closed feasibility constraint. So this is a very general mechanism, a clock auction that adapts to any feasibility constraint that it might face. And in terms of information limitations, it matches, it shows that essentially that one instance that seemed to be very simple and causing already a lot of harm is actually as bad as it gets, that one can actually match this even for highly complicated feasibility constraints. So that provides one first positive result on how one can actually design clock auctions for these general settings. And then the second positive result, the point of it is to provide with some insight regarding how to use randomization, how one can possibly use randomization to go further, because the first two results actually wrap up what can be done with in terms of prior free deterministic clock auctions. That's kind of essentially solved. But much less is known regarding what one can do with randomized clock auctions, where the worst negative result is just a small constant, and we still have very limited positive results on the other end. So this is wide open and one of the most exciting open problems in this area. Let me jump in and kind of talk about the negative result first. So this result essentially is based on the following simple instance. Let's instantiate it thinking about the seats in an airplane, since we've talked about this before. So let's assume we have n-1 seats in an airplane, and then we have n-1 individual bidders, each one of which wants just one seat, right? So each one of those are different bidders, n-1 distinct bidders, each one wants just one seat. And also we have one more bidder, think of it like a team that might want exactly all n-1, that wants exactly n-1 seats. So they would like to book the whole plane. So again, that's one bidder that wants all the seats. The other end, there's n-1 individual bidders, each one only requiring one seat to be served. So from an algorithmic perspective, this is a trivial problem. You can just see what's the only choices we have. There's just two maximal sets: either serve all the individual bidders or serve the team of the multiple of one bidder, multiple seats. Just figure out which one gives you the largest value. However, as it turns out, that instance alone is enough to cause trouble for deterministic prior free clock auctions. And all I'm going to do here is provide some intuition regarding what is the obstacle that these auctions face. And in fact, even if I told you that the bidder, if I told you the value of the bidder that represents the team, that doesn't make life that much easier. So the issue is that in a clock auction, the only way to probe the total value of the individual bidders, if we knew, is it more than one or is it less than one, that would suffice. But the only way to check whether it's more than one or less than one is to approach one of the bidders and raise their price. Let's say start from a very low price and then raise it gradually, and then try to see if they're willing to go higher. That's the only way to check whether someone's value is higher than a specific threshold or not. But unfortunately, if the auction is deterministic in an adversarial world, you can imagine that the values might look something like that, like a harmonic, let's imagine. It's not exactly what the lower bound is using, but it captures the rough intuition. So imagine that you approach the bidder at the bottom, the one who has the lowest value. You try to raise their price, they drop out. Then 1 over n minus 1 is a low value. You end up losing them. And then let's say you proceed without, because it's deterministic in an adversarial world, you might end up proceeding and raising the prices from the bottom bidder first. And the issue that arises is that to discover people's values, you're essentially losing many of them. You keep losing them before you are able to see the total value of that set. And although it's a lot, it's a harmonic, so it's logarithmic total value, log n essentially. You cannot really verify this because you keep losing. You're raising a price. You at the end of the day you'll realize it, but you only realize that after you've rejected all the bidders. And the intuition to take away from this is that discovering lower bounds for people's values in clock auctions is costly. You need to risk losing them to figure out if they're willing to pay a higher and higher price. So as you're raising the price, you always risk losing them, and that's what this instance captures. And the question now is, okay, this essentially provides a very specific instance. How can one design a positive result for a wide array, for any feasibility concern? How can we even describe what would be the right way of raising prices deterministically in a prior-free world without for any possible feasibility constraint that one could provide? And this is where this water filling clock auction comes into play. This water filling clock auction was inspired by an auction that's somewhat similar by Babayev et al., a very nice paper by Babayev et al. And what it does essentially is that it pretends, it starts with posting small prices to everyone. Let's say a price of 1. Let's imagine that this is low enough, that we know everybody would accept that. And then gradually raising the price. But how do we raise? How do we choose who to raise the price to? Well, what we do is we actually pretend that the prices are actually the value. In other words, we find the optimal revenue set. Like if we were to stop now and accept one of these, which one would give us the highest revenue? If you check in this case, it would be the blue set, would give us a maximum revenue of 4. And then what we do is we freeze all the prices. We don't touch any of these prices. We don't raise them at all. And then look outside that set and try to find which is the smallest price and raise it. So in this case, we fix these prices. We go outside and we see that all the prices were 1. We raise them to 2 and repeat. Now we have a different set of prices. We go again. We find what is now the set of maximum revenue. It happens. Oh, by the way, well, I should have mentioned that as we do that, we might actually lose people. Once we raise price to 2, this bidder at the top left actually drops out. And once we raise these prices, we go back again. Now the maximum revenue is actually 6 instead of 4, because we see that orange feasible set, the total revenue in it right now is 6. So what we do is we go outside that feasible set, see who has the lowest price. You see that the bidders in the blue set are the ones who are currently only facing a price of 1 each, and we raise that price. Again, that could lead to someone dropping out or not. In this case, it doesn't, and we just repeat. Again, now with updated prices, blue wins again. Their maximum revenue is 8. Note that the maximum revenue is weekly increasing because we never risk losing the feasible set that gave us the maximum revenue in the previous iteration. We fix that, and then we raise prices outside. If we see an even better one in the next iteration, we freeze that and proceed, right? So we weekly increase the maximum revenue. And again, as we raise the prices, we might lose someone. In this case, the second one in the bottom row, a bidder drops out. We update, and we just observe now who is giving us the maximum revenue. It's again the orange one, and we just proceed. The auction just proceeds by always raising. And the reason it's called a water filling clock auction is because it's always raising the smallest price. It starts from the bottom price outside the maximum revenue feasible subset. So if we keep doing that just to simulate this until the end, what we get in this particular case is that the only bidders that are going to survive are the ones that are now surviving in that green set. So these are the 2 bidders that survive, and they're paying the price, the last price that were offered, which is 6 for the first one and 3 for the second one. And in fact, the way we show that this, I should mention that the 2 main differences compared to the Babayev et al. Mechanism is, one, that they're not raising, that this auction is not raising the price of everyone outside the maximum revenue set. It's only raising the bottom one, hence the water filling aspect of it. And the second one is not doubling it. That Babayev et al. Auction doubles the prices outside, which now we're not doing. We're raising by an increment, the same increment every time. When in this case it was 1, but you can imagine you can make that as small as you like and simulate the auction. And these are the winners. And in fact, what we show is that not only the value, but the maximum revenue is what gives us the revenue we achieve in the end. In this case, 9 is what guarantees an approximation to this, the claimed approximation of the optimal social welfare. And specifically, what it achieves is the 4 log O approximation, which is better than 4 log N, I should mention. O is the size of the optimal feasible solution, means all the number of bidders that are in the optimal, the social welfare maximizing solution. Of course, these are at most N, at most everyone. And we achieve a 4 log O approximation, and that is guaranteed for any downward closed feasibility constraint, right? And as I mentioned, that we actually guarantee that the maximum revenue, note the maximum revenue is always a lower bound for the welfare that we achieve, right? So since we achieve the revenue of 9, it must mean that the social welfare is at least as good, otherwise these people would have dropped out. In fact, in this case, the optimal welfare, the welfare we achieved is 11, right? And in fact, as I mentioned before, if one would be concerned about computational constraints, with this actually works in if at each round when we're trying to figure out what a feasible subset maximizes revenue, we can use an approximation algorithm that uses, an alpha approximation algorithm for computing this. If it's a hard problem, then we get a 4 alpha times log O approximation. So we suffer the same loss in approximation if we want to also add the computational constraints on top of it. But again, our main focus is on information constraints, which, by the way, in the lower bound that I mentioned before, it's purely information constraints. From a computational perspective, that problem is trivial. So it's all about the limited way in which clock auctions can access the values of the bidders, and this is the reason that causes the negative result, the inapproximability. So this is the main result that shows the water filling clock auction actually, no matter what feasibility constraint you throw at it, it matches this logarithmic bound. In fact, not just log N, log O, and is therefore optimal. But what I want to wrap up with, kind of this first part of the tutorial, is randomized mechanisms, and because this is the part that's wide open. We don't yet know what's the limit of randomized clock auctions. What can we do? How should we use randomization in a prior-free world to decide how to raise the price whose price to raise at each step? Maybe how much to even raise. Maybe we can raise the same price consecutively multiple times. How should we use randomness, and what guarantees can we get? I really think this is a fundamental open problem that requires a deeper understanding of a setting, which, by the way, if someone's not interested in mechanism design specifically, this question is purely algorithmic. If you're given this particular way of probing people's values, you just raise this threshold and they stay in only if their value is higher than the threshold, then there's this hedging element to it, where whenever you raise a value, you risk losing that participant. And the question is, how should you raise? How should you decide the trajectory in which you raise prices and balancing that risk of losing people to achieve good worst case guarantees? So this is a purely algorithmic question at this point that we don't understand how to solve. What's the limit of it? And one thing I want to also point out is, in this case, the lower bound, remember, that gave us a logarithmic lower bound for deterministic prior-free clock auctions. If we were to use randomness, this becomes trivial, right? Just flip a coin and decide whether to serve all the people on the left, and -1 individual bidders, or the team on the right, without even asking them for the values. You can just, decide who you're going to reject, just raise their values until they go out, and then serve the other group. So easily you achieve a half approximation, a 2 approximation, because no matter what, with half probability, you're definitely going to get the right set. So this is a very tempting reason to believe that with randomization, you could actually do much better. Definitely this lower bound goes away really quickly. But how should we use randomization? And the main result here that we achieve with randomization is that we simultaneously match the log O guarantee that we get with the deterministic prior-free clock auction, but at the same time get a root log K guarantee, where K, remember, is the number of maximal feasible sets. So if you're given an instance where K is smaller than N, let's say, this actually gives you better than log N. It gives you an asymptotic improvement. And in fact, note that the lower bound only holds for K equals 2. It holds even, rather, for K equals 2. So it's unbounded as a function of K. We get a log N lower bound for K equals 2. Here we actually are able to bound for a superset of instances of that negative result. So that generalized the negative result that gave that we discussed before for deterministic clock auctions. We get an asymptotic improvement. So for all these instances where K the number of maximal feasible sets is less than n, we get a root log n bound this way. However, it is still wide open. This is an improvement. And in fact, I'm going to mostly discuss how we achieve this, just to provide an initial insight regarding how randomness could be used in the context of clock auctions. But we don't have a good understanding of what can be done. And that's what I think is the most exciting direction for future research. And similarly, in the next half of the tutorial, the same question applies for priors and how to use priors. And Dan is going to be discussing this. So let's now briefly wrap up by discussing how we're going to use randomness. And we're going to first talk about the sampling auction. So here's a very simple way to use randomness. Just randomly sample the values of bidders and choose the set of optimal sample value. And you might wonder, how do we sample? What does that even mean? Well, what it means is you can randomly decide, choose some subset of bidders in advance, and then just raise their prices until they drop out. So essentially, in doing so, you lose these bidders. You cannot serve them. They're rejected. However, you learn their values, and you can use that as some kind of discovery. You learn something about the values in a randomized way. So one thing you can do is then use these values after these people are out of the auction, use what you've learned, how far they were actually willing to go, to decide what sets seemed to work well, using that as a guide. So in this case, again, if you check and you sum up the values, only the green values, the ones from the sample, you'll see that blue would be the feasible set with the largest value according to the sample. And then this sampling auction would just choose these. So this is a clock auction, and it might actually perform well in some cases. For instance, if the value is very well distributed, maybe the sample is representative, and then you learn something, but it's not hard to verify that this can actually fail miserably in some cases, right? So on its own, this auction can be horrible. Specifically, if the value, the social welfare, is concentrated on a small subset of bidders, just to be extreme, let's consider it's just one of them. Let's say the bidder on the top bottom left has a value of 1,000. Well, the only way, there's two things that can happen. Either that bidder is part of our sample and we realize there was a lot of value to be made there, but now since that bidder was sampled, we cannot serve him anymore. So that's a horrible outcome in terms of performance, because the others are not high enough to reach a reasonable social welfare. Or we're not sampling this bidder, and then there's no reason to think that that gray subset is actually any good. So there's no reason to choose. So in both cases, the sampling auction would fail to achieve a good approximation. However, the main result, which I think is a guide regarding what kind of result we should be seeking, is that this, if you think about it, this is actually complementing in a very nice way the water filling clock auction. The water filling clock auction failed when the value was distributed across multiple bidders, and then every time as the price was being raised, the discovery was costly. It was losing significant value as it was discovering which subsets to serve. Whereas this one actually works in exactly fails in the complementary way and works in a complementary way. So specifically, the water filling auction and sampling auctions are complementary in the following way. The water filling clock auctions gives a poor approximation when the value of the optimal set cannot be concentrated on too few bidders. So in other words, if there was, let's say, a single bidder, the water filling clock that had all the value, the water filling clock auction would eventually never reject the bidder. We would identify that bidder. In fact, even if there were just a few bidders that are concentrating all the value, we would essentially see that as revenue, and we would get a really good approximation. That's the intuition. Given time constraints, I can not go into too much detail about this. But as it happens, when exactly the sampling auction fails, the water filling clock auction succeeds, and vice versa. And using that intuition, we actually this result on randomized clock auctions uses the hedging auction, which does the following. It says, I'll randomly, with probability half, I will run the sampling auction. With probability half, I will run the water filling clock auction. And as it turns out, this is the auction that can actually give that best of both worlds, essentially, of maintaining the worst case guarantee of log O, but at the same time, if K is small, if the number of maximal feasible sets is small, it actually performs much better. So to summarize, when it comes to deterministic prior-free clock auctions, I would argue that this part is kind of essentially settled. Given the recent findings, we know exactly what the optimal auction is. However, when it comes to randomized clock auctions, we have some initial ideas, and this last auction that I discussed provides some insights regarding how one could proceed to use randomization to do better, but we don't have a full understanding. And this is the main open problem. What is the best approximation achievable by a randomized clock auction for downward closed visibility constraints? That's the wide open question. I want to emphasize that the best known in approximability result is just a small constant. So we cannot even at this point rule out that a constant is achievable for any downward closed visibility constraint. I don't know if I actually believe the constant is the right answer, but everything is open. So the state of the art is what I presented so far. And also, apart from going for the main question, any downward closed visibility constraint, there's many interesting special type of feasibility structures that one could focus on. For instance, if one were to focus on knapsack constraints, for which again the negative result holds, if you were to try deterministic prior free clock auctions on knapsack constraints, one cannot do better than logarithmic. However, with randomization, it's easy to achieve a constant. Specifically, you can do the following. You can flip a coin to decide whether to, one, rank by density. Remember, in the knapsack setting, every bidder has a specific size request, how many seats, let's say, they request from the plane. And then what rank by density does is essentially it increases each bidder's value in proportion to the size of the request, in proportion to the number of seats that they request. That's one thing you could do. Or alternatively, you could just uniformly raise the prices and just accept one bidder, the one that has the single bidder that has the highest value. So if that reminds you of something, probably it is the fact that the randomized, the approximation algorithm for the knapsack problem itself, where you either rank by density or accept the highest value. And that's exactly the same argument that allows you to show that, you know, with randomized clock auction, knapsack actually becomes much more tractable. You can achieve a constant. But there's interesting constraints that are special. For instance, single-minded bidders, you know, the spectrum auctions example that I mentioned before would be an interesting special case of a specific downward closed visibility constraint for which we do not know what the right approximation guarantee would be. We don't know if we can achieve a constant or not, or what's actually the optimal bound. And with that, let's wrap up the first part of the tutorial, and then Dan will proceed in the second half discussing, similarly in a very analogous way, what can we do if we have prior information, distribution information regarding the values of the bidders. Thank you.
Hi again, everyone. We'll be starting part 2 by picking up where we left off and continue to think about designing forward clock auctions in general downward closed settings. However, in part 1, we made the assumption that we had no prior information regarding bidder values. In practice, however, we often do have some distributional information or data regarding bidder values, and we want to think about how this information could possibly be useful to us in designing clock auctions aiming to get better social welfare guarantees. In fact, we can think about first taking a cue from a more common assumption in economics and auction design, particularly that we know the entire distribution from which a bidder draws their value. An interesting question then arises in how a clock auction should leverage this distributional information in a principled way. For example, perhaps the prior information can be used to guide the price increase process in a highly complex way, but we have some considerations to make. If a bidder's value distribution has high values in the support, perhaps you want to push their clock more quickly to discover if the true value is high. But you may also wish to avoid pushing the clock too far, since you might risk losing the bidder and losing a lot of potential value. So we really want to think about this information seems like it could be really useful, but how can we use it? And for this next portion, I want to present an initial possible way that we might use the prior information, but I want to preface the whole section by saying that the approach is far from the most sophisticated ways you may come up with, and represents only really an initial step towards studying clock auctions with prior information, and there are many interesting questions to be studied here. But to get us in the right headspace, suppose that we're in a setting where we have full access to the prior distribution of each bidder. In other words, we know that each bidder draws her value independently from a distribution, and we know the distributions. If we know all of the distributions, observe that we can infer many statistics of interest. For instance, we could infer the benchmark welfare that an optimal auction might be able to achieve, and we can also infer expected posterior values of bidders given that they've accepted some current price. So there's a lot of, this tells us a lot. And with access to this full prior information, we can actually achieve much improved bounds compared to what Vasilis showed us earlier, even with a really simple class of clock auctions that only use the prior information in a really basic way. And we call these auctions single price clock auctions. Single price clock auctions offer a single price to each bidder simultaneously, observes the responses of the bidders, and selects a winning set from among them. To see an example, imagine that we have these 4 disjoint maximal sets, each represented by a different colored box here. The value information is, of course, private, but the distributional information in blue is public to us. Using the structure of the feasibility constraint, which is public, and the public distributional information, a single price clock auction computes a vector of prices, broadcasts the vector of prices to all the bidders simultaneously, and bidders can choose to accept or reject their price offer. If they reject, of course, they'll drop out of the auction as we saw before. At this point, we can choose to serve any feasible subset of the remaining bidders. For example, maybe we serve the bidders in the bottom right gray set since their sum of accepted prices is highest, or perhaps you use conditional expected value or some other statistic that you want to calculate based on the prior distributions. But regardless, any feasible subset of bidders who have accepted their price, you can accept them. So this auction format is really, really simple and is only sort of basically using the distributional information in a very straightforward way just to compute the prices in one round. And yet, even with this simple auction form, we can obtain much improved bounds relative to what Vasilis showed us earlier with the hedging auction. And the formal statement of what we show in this paper studying single price clock auctions is somewhat technical, but essentially you can show that if you offer one of log k uniform prices, in fact, the one with the highest expected welfare, you can obtain a log k approximation to the benchmark welfare. And all of these prices can be inferred from the prior distributional information. And one way to think about this result is to imagine that we had to offer a uniform price to all bidders. If we offered a high uniform price, we could potentially be losing many bidders, but any bidder who accepts their price, we know that they must have a high posterior expected value. So we could potentially be learning a lot by offering a high uniform price. On the other hand, if we offer a low uniform price, we don't learn very much at all, right? We may not even be learning too much about what bidders' values are. We may not be eliminating many values from the support. However, we might keep many more bidders than we would if we had offered a high uniform price. And these both have pros and cons, but you can show that if you decompose the benchmark welfare into 2 cases, one where there exists some small feasible set of bidders that contributes a lot of welfare and expectation, and one where only large feasible sets of bidders have total welfare close to the benchmark, that high uniform prices cover these cover these small feasible sets of bidders, whereas low uniform prices cover the case where only large sets of bidders have high total welfare. And the above single price clock auction at the top of the slide, which selects the best of log k different uniform prices, essentially covers these 2 cases separately, right? So p equals 0 is certainly a low uniform price, whereas this p equals delta times 2 to the 1 minus j, you can think of delta as a really, really high, high benchmark or high target that we compute from the prior information. So what's interesting is that this single price clock auction actually is not using the distributional information in a particularly sophisticated way and is actually really, really simple and may resemble a class of mechanisms that you're familiar with, the class of sequential pricing mechanisms, right? Because in a single price clock auction, the auctioneer makes only a single offer to each bidder. So they're closely related to this literature that's very broad in EC on profit inequalities and sequential pricing mechanisms. In a sequential pricing mechanism, bidders are also only offered a single price, but they're approached one by one and offered take it or leave it prices. So if they accept the offer, the auction will serve them. So there's an interesting question here. regarding deferred acceptance versus adaptivity, right? Because clock auctions can leverage deferred acceptance, single price clock auctions included. Sequential pricing mechanisms have to commit to serve a bidder if they accept their offer, whereas single price clock auctions observe the responses of all of the bidders and thus defer the acceptance until the very end of the auction. On the other hand, sequential pricing mechanisms can rely on the responses that bidders have reported already to adapt offers to bidders as they approach them one by one, whereas a single price clock auction sends the single offer to each bidder simultaneously, so pricing is non-adaptive. So there's really interesting questions about the relative power of these two tools, these two algorithmic tools of deferred acceptance and price adaptivity. And as it shakes out, for general downward closed set systems, deferred acceptance is much more powerful than adaptivity. So a sequence of papers showed sort of related results, but you can infer from all of them that there's an omega log k over log k lower bound on the performance of any sequential pricing mechanism in a downward closed set system with k maximal feasible sets. Whereas if you recall on the previous slide, the single price clock auction that I showed you obtains a log k approximation to this optimal social welfare. So in general downward closed feasibility constraints, or general downward closed set systems, deferred acceptance turns out to be exponentially more powerful than adaptivity. However, in more structured settings, comparing these two tools is wide open. We don't know necessarily if single price clock auctions are much more powerful than sequential pricing mechanisms in more structured combinatorial settings. And I want to just point out some open questions here, right? Although single price clock auctions do obtain an exponentially improved guarantee relative to sequential pricing mechanisms and what we saw before, you can actually show that this log k guarantee can be recovered using a prior free randomized clock auction, in particular the hedging auction. So perhaps there's a way to use prior information in a much more sophisticated way and actually do much better. In fact, I think that's a really fundamental and interesting question about asking what the best approximation you can achieve using a clock auction with prior information in general downward closed settings. For all we know, the answer could be a very small constant because the best known lower bounds are only small constants. As Vasilis also stated for randomized auctions, the same is true here. But also, I think this question remains interesting if you think about structured combinatorial settings. If you have a combinatorial auction with single-minded bidders, or you have a setting where the feasibility constraint corresponds to a matching in a graph, can we achieve really much better approximation guarantees using clock auctions with prior information? All of these set systems are kind of wide open. And finally, if there is a separation between single price clock auctions and general clock auctions for downward closed settings, I think that would also be a really interesting result. And then that leads us to a broader class of questions of how does the number of rounds of interactions, in other words, how many rounds of price increases can you use, how does this affect the approximation guarantee of a clock auction? Is it affected by the number of rounds you can ask each bidder or the number of rounds in total? Can you get approximation guarantees that are parametrized in sort of the bounds of the number of rounds of interaction? I think all of these are really fascinating and important open questions from both a theoretical perspective, because we really have no idea how we should be using prior information in a more sophisticated way, and also really practical questions. I think all of these are. But we'll just pause here for a brief moment to wrap up sort of forward auctions, and feel free to ask any questions in the chat, because moving on, we're going to be sort of flipping the auction on its head and consider a reverse auction setting or a procurement setting. And to get us in the right headspace, let's start with another example, where you imagine that you're a government employee assigned to the construction or renovation of a government building. You're thus tasked with hiring several different service providers from a set N to handle different aspects in the construction. You have a value for the service that each provider offers, and moreover, a value for each subset of providers that you can hire. For instance, this valuation could be additive, in which case the blue boxed set would provide you a total of 5 plus 5 plus 7 equals 17 value. Note, however, that your valuation V need not be additive and can map subsets of n to non-negative real values. For example, the valuation function V could be additive or could be more general, could be submodular, or even more general, subadditive. Each of these captures gradually wider classes of valuation functions. On the other hand, for any of these valuation classes, if V is monotone, it's easy to figure out what set of service providers to hire. Hire the entire set n. But of course, that's not realistic. We again face a feasibility constraint. The providers have a cost which they must be compensated in order to provide their service, and the government's only allocated you a finite budget B. So your goal is to maximize your valuation given this budget constraint. And I want to point out that even for the smallest class of valuation functions, additive valuations, this is already an interesting and B-hard optimization problem, the knapsack problem. However, regardless of the valuation functions, we can again define the set calligraphic F as the set of feasible outcomes. In this case, it's the collection of sets of providers that you can afford. Or in other words, the collection of sets of providers whose sum of costs is less than or equal to your budget constraint. And we can, analogously to before, define opt as just the value of the best set that's feasible. And our goal, once again, is to output a feasible subset of comparable value to opt. And even just the algorithmic hardness of this problem is interesting and has been well studied. And there's many different approximation algorithms for all of these evaluation classes and different oracle models proposed in the literature for accessing the values of V on different subsets, like the value query model and the demand query model. And all of these are interesting in their own right. However, of course, this is a tutorial on mechanism design. So we want to think about the mechanism design version of this problem, where the costs of the providers is unknown, and we still want to maximize our valuation function despite this lack of information, right? So just in contrast to the setting before, now the valuation function is public information. It belongs to the auctioneer and it's public. All the bidders even know it as well. But what's private information is the costs of the bidders. And this is still a binary single parameter setting because bidders are either has their service hired or not, right? So they're either in or out. And the setting is single parameter since they only have one piece of private information, their cost. And this is exactly, if we want to think about designing mechanisms for this problem, the budget feasible auction design problem proposed by Singer. The cost of each of the service providers is private information, and we have to somehow elicit the costs from the providers. So if we thought about designing a sealed bid auction for this problem, it would be sort of very analogous to what we saw before, except instead of asking for values, the auctioneer would ask the providers to report their costs in the form of bids, and then would use these bids to decide who to serve or who to acquire and what payments they should be awarded. And of course, we obviously want strategy proofness like we did before, which means that bidders maximize their utility, the payment that they get by true reporting, or payment minus cost by true reporting. But the tricky thing about this mechanism design problem, which makes it, I think, interesting in its own right, even beyond clock auctions, is that the budget feasibility constraint is on the payments to the bidders, not the true costs. So the feasibility constraint and the incentives are actually intertwined in a really non-trivial way, because your mechanism has to be budget feasible with respect to the payments that it's awarding in order to ensure truthfulness. Whereas opt is unrestricted by this. Opt knows the true costs. But of course, we don't want to design just a sealed bid auction. The whole purpose of this tutorial is thinking about obvious strategy proofness. So we want a clock auction. So let's think about what that might look like here. And again, it's going to look very similar to what we had before, except instead of ascending price trajectories, there's going to be descending payment trajectories. So perhaps each bidder faces a clock payment offer equal to the budget at the outset, and these payments gradually descend over time again, could be uniform, but need not be. And bidders eventually will drop out when their payment is less than their cost, right? And that will continue until we arrive at a feasible subset. And recall that the feasibility in this problem is with respect to our budget constraint and the payments. So since 15 plus 35 is less than or equal to our budget, the auction terminates here, and green and orange are served or acquired at these payments. So I want to take a moment now to think about how we might design clock auctions for this problem and give you a couple of seconds to think about it yourself. Even just for the smallest class of valuation functions we mentioned, additive valuations. Under this class of valuations, we essentially have just the knapsack problem where the sizes of the goods or the costs of the bidders in the auction version is private and unknown. So if we think then about what clock auctions effectively let us do, they don't allow us direct information to the private costs the way sealed bid auctions would. But they allow us to probe costs in a gradually decreasing fashion. In other words, we gradually obtain better and better upper bound estimates on bidders' private costs, and therefore better and better lower bound estimates on their bang per buck. So with this intuition in mind, you might start to be thinking about sort of bang per buck. It looks like a knapsack. You may want to think about a natural approach that's kind of akin to the greedy algorithm for the knapsack problem, and decrease clock payments in proportion to the public value. And then you just can terminate the auction when you arrive at a feasible set. Unfortunately, it's not too difficult to construct an instance where this kind of approach doesn't work out. So for example, if green has a value 1 plus epsilon and blue has a value b, at the point where the clock payment offered to green is 1 plus epsilon, it will be b for blue. And if we continue to decrease both of them uniform or in proportion to their value, blue will drop out and we'll get green only obtaining a value 1 plus epsilon where we could have gotten a value b. So we can refine this idea and build in sort of another notion from the classic two approximate greedy algorithm for knapsack and stop our payment lowering a little bit early, like when removing the highest value remaining bidder yields a budget feasible set. So just to imagine what this might look like, imagine that the bidders on the bottom here are sorted from left to right in non-increasing order of their bang per buck value over private cost. By decreasing payments in proportion to the public value, we're essentially raising a bang per buck bar, which bidders are going to reject in reverse order of their value per cost ratio. And we'll just terminate a little bit earlier than we did before. So we can imagine raising this bar over time until we arrive at a set that's just infeasible, right? We have one more bidder than we would like. So there's a subtlety here. We can't stop the auction yet because outputting all the remaining bidders is not feasible. So who do we choose? And you can actually show that without too much work and maybe a back of the envelope calculation, that if you either pick all of the low value bidders or the single high value bidder remaining, you'll get a 4 approximation to the optimal social welfare. So at least for additive valuations, it looks like clock auctions can do pretty well. But the vast majority of the literature on budget feasible mechanism design doesn't really study additive valuations and instead turns towards more general valuation classes, in particular monotone submodular and submodular. And I'm just showing sort of a sequence of papers that all study submodular valuations and the state of the art in this blue box here. And I want to point out a really notable gap between the performance of deterministic sealed bid auctions and randomized auctions, right? All of these are sealed bid auctions, by the way. Using randomization, we know how to obtain constant approximate sealed bid auctions, but without randomization, no auction achieving a non-trivial approximation was known. In fact, in an EC 2019 paper where they proposed this first constant approximate randomized sealed bid mechanism for general submodular functions, Manatidis et al. Stated that beyond additive valuations, we consider obtaining deterministic budget feasible constant approximate mechanisms or showing that they don't exist to be the most intriguing related open problem. So if we want to think about how we're going to be designing a clock auction, and in particular how we're going to design maybe a deterministic clock auction, what are really the challenges that we're going to have to face? Why is determinism so difficult for this problem, and why might clock auctions have difficulty too? Well, beyond additivity, even monotone submodular valuations turn out to be more difficult. In particular, additivity guarantees that the marginal contribution of I to a set S or a set T is the same. In other words, V of I union S minus Vs equals V of I union T minus Vt for any two sets S and T that I is not contained in, right? On the other hand, for submodular functions, the value of a bidder actually depends on who we eventually accept, right? The marginal contribution of a bidder to our final set depends on who we're going to accept. And this makes it really difficult to sort of adapt our similar approach for clock auctions for additive valuations to this setting with monotone submodular, right? Because we have a chicken and egg problem. We don't know which bidders we're eventually going to accept. So how can we really gauge the value of a bidder in an attempt to sort of decrease in proportion to their value? Even worse, at the outset, if you think about the marginal contribution of a bidder to the entire active set of bidders, all of the marginal contributions may be zero because they may cover each other. The value may cover each other in very overlapping ways. So if we want to design a clock auction, we really need a pretty different algorithmic technique here. And if we want to try to get rid of randomization, let's try to think about why sealed bid auctions really turn to it so frequently. So if you think about designing a sealed bid auction for this problem, a natural approach is to accept the costs as the bids from all of the sellers, and then run a forward greedy maximization algorithm given these bids. So what might this look like? Well, you could sort bidders recursively in order of their marginal contribution to the current set of the reported costs, the bids. You could then define the payments via Meyerson and output the better of this solution and the single highest contribution bidder. This is sort of a auction analog of sort of a natural forward greedy approach for monotone submodular valuations. Unfortunately, if you just try to compare these two solutions, you break truthfulness. This is no longer monotone, right? So instead, you could try to randomly choose one of several ex post solutions, and that's essentially what all of the sealed bid auctions use. They randomly output the result of a forward greedy algorithm or the best singleton bidder. So in thinking about how we want to design clock auctions, in particular deterministic clock auctions, we have two challenges that we need to think about facing. One, how do we design price trajectories for a clock auction or payment trajectories for a clock auction when we don't even know the ultimate contribution of any individual bidder? And two, how do we get around the need for randomization without breaking monotonicity? So we ideally need to answer both of these questions if we want a deterministic clock auction. And as we're going to show shortly rather, thinking about these two questions separately is the wrong approach. Because by leveraging the structure of clock auctions, we can actually circumvent the need for randomness altogether. And I think this is just a really interesting insight that I want to pause on for a second. Sometimes thinking about the implementation of clock auctions can lead you towards an algorithmic insight that you may not have thought about if you were just thinking about the direct revelation sealed bid version. But to see the insight that we can use, how we can use clock auctions to get around the need for randomization, let's examine an intermediate ground between the full information setting, where all of the private costs are known, and our true fully unknown cost setting, and assume that the buyer knew the value of the optimal solution. In other words, the buyer is told by some genie that V is the maximum value she could obtain if she knew all of the private costs. What we can do with this information is we can try to build a set of providers H that we hire gradually over time, one at a time, by approaching bidders one by one and offering them take it or leave it offers. In other words, like a sequential payment mechanism. And we can do this from the active unhired provider set A. And just some notation, we'll use this notation of V of I given H to denote the marginal contribution that bidder I has to set H. And at each step of our procedure, we're going to approach the bidder with the highest marginal contribution to our current hired set H. In other words, in this first phase, the highest singleton value bidder. Let's suppose that this is the yellow bidder. If we aim to reach a value of V, if we could only offer a take it or leave it offer, what should the payment offer be? Well, it should clearly depend on the value of yellow in some respect, right? For instance, if the value that yellow had was equal to opt, we should just surrender the entire budget to them. On the other hand, if it's really small relative to opt, we definitely have to save budget for the other providers. So a natural option might be to look at what fraction of the optimal value they may be contributing and give them the corresponding fraction of our budget. And suppose that yellow were to accept this payment offer. We can then add yellow to our hired provider set and move on to the next provider who has the highest marginal contribution to the updated set. Suppose that this is the dark gray provider and that gray rejects this payment offer. Then we can permanently discard gray, and gray is removed from the active set A and not added to H. Then suppose we approach the next bidder in the order and it's the light blue bidder who has the next highest marginal contribution to the unchanged set H. And suppose light blue accepts the offered payment. Then unsurprisingly, we add blue to H and continue on down the line. And if you use this approach with some slight modifications, for example, doubling the payment offered to each bidder, just to avoid some bad edge cases, you can obtain a good approximation. In the case of monotone submodular valuations, a small constant approximation. But there's a big assumption here. We need to know that opt is equal to V in order to get this kind of approach to work. And a few of the papers in the literature that propose sealed bid auctions, randomized sealed bid auctions for this problem, utilize a similar kind of approach to discard half the bidders uniformly at random to obtain their true costs in a strategy-proof way, and then use these costs to estimate opt, right? So they take like a random sampling-based approach. But without random sampling and without prior information, how can we obtain an estimate of the optimal solution? You can actually do this by leveraging the structure of clock auctions. And I think this is a really interesting point about designing clock auctions, or more generally, thinking about designing mechanisms with implementation in mind. I want to reiterate that sometimes thinking about the implementation itself can lead to an algorithmic insight that answers a question that is open. What are we going to leverage about clock auctions to actually achieve this? Well, just the structure of clock auctions. Since we don't need to just make one single offer to each provider, we can instead offer a series of decreasing payments as we slowly increase a lower bound estimate of the optimal value. In other words, we have a kind of primal dual approach where we can gradually discover better, larger lower bounds on opt over time, which then in turn imply decreasing payment offers. But what is this going to look like in reality? Well, most of what our auction looks like should hopefully be pretty familiar. Instead of the exact value of opt, we'll have a lower bound estimate of opt tilde. But I'll note that we can always ensure that this original value of opt tilde v prime is something we know we can achieve, right? It's a technical point, but you could just take v prime to be the highest singleton value of any bidders. But other than that, the rest is essentially the same as before, right? We've just replaced opt with opt tilde. I'm now showing the central important difference that's really going to allow us to leverage clock auctions. We're going to maintain two sets rather than one. In addition to a current round set H, which will operate the same way as it did when we knew the value of opt, we're going to maintain a hold-aside set H prime. This hold-aside set H prime is going to operate very similarly to how holding the set aside in the water-filling clock auction for forward auctions that Vasilis presented earlier operated there. It basically is going to secure us better and better guarantees. But we'll see how H prime works exactly in this setting and discuss its purpose more concretely on the next couple of slides. But at each phase of the auction, we're going to proceed exactly as we did before, where we knew the value of opt. Instead, we're going to be using our lower bound v prime in place of the true value. Suppose that's the yellow bidder, and we offer her this payment, and that she accepts the current payment offer. We can then add yellow to the current round set h and compare the value of h to our lower bound. Suppose that adding yellow to h causes us to reach the target, then we can double the lower bound on the optimal value and add the yellow provider to our hold-aside set h prime. In each phase, we won't consider anyone in h prime, which means in the following phase, we're not going to change the payment offer to yellow. This is kind of exactly the same way that in the water filling clock auction, we only increased prices outside of the current winning set. And much like in a water filling clock auction, having this hold aside set h prime allows us to secure the value inside h prime, and we know that we're not going to lose any of the providers before we reach a better updated target. And our updated target in this case is going to be 2 opt tilde. We're just going to double the target. Let's say light green now has the highest marginal contribution to the now empty set h, and that green accepts her payment. We're just going to proceed exactly as we did before, adding green to the current round set and continue onward. Suppose orange is the next provider, and that orange rejects this payment offer. Then orange is going to permanently exit the auction, and we're going to move on to the next bidder. Suppose that's dark gray, and that dark gray accepts the payment offer. We can then add dark gray to h, and suppose this now leads the value of h exceeding our lower bound. In other words, now we know we can secure something that's at least 2v prime. Well, now we can return yellow back to the active provider set and replace our old h prime with our current set h. This is exactly kind of the same thing we did in the water filling clock auction, where the set that we were holding aside and not touching the prices of was changing over time. In this auction, we've now secured the value of the green and gray providers, since we're not going to change their payment offers in the next round, in the next phase. We'll also update our lower bound estimate again, doubling it. And you'll notice again that we're just doubling the lower bound on opt. And in each round, we choose to double it because it balances two things. If you increase too quickly, maybe you would overshoot the true value of opt and offer payments which are too low, possibly causing all providers to reject their offers. And if you increase too slowly, you could lead to too many rounds before honing in on the optimal price, which increases the chance that we offer optimal providers low payments due to their value overlap with non-optimal ones. So I think this is a really interesting algorithmic question about what the right parameters of a clock auction are, but understanding the minor details of why we're doubling is not really particularly important. Mostly the structure itself is. And beginning in the third round, we can again approach the yellow provider and compute the new value of her payment. If this new value of her payment is lower than her previous clock offer, we can just descend her payment to this new value and continue our auction. So in this way, we're actually using a clock auction, lowering the payments over time. And if this payment offer is lower and yellow accepts her updated payment, we can then add her to the current set and unsurprisingly continue as we did before. Possibly light blue will reject, and finally we'll offer a payment to light gray and suppose that she accepts. Or now I want to point out that the active unhired provider set A is empty. All the remaining providers are in H prime or H. And with the payments we have right now, we can use whatever algorithm we want to find any budget feasible subset of providers, output that set, and set the remaining payments equal to 0. And that's, again, just another really interesting feature of clock auctions compared to other mechanisms. Once you have a payment, you can use whatever algorithmic tools you want behind the scenes, because bidders just face this very straightforward payment or price trajectory. And this is, with some very slight modifications to improve the approximation factor, exactly what our clock auction format in a recent soda paper does. The key feature in the proof is to demonstrate that although you don't know the true value of opt, our lower bound eventually gets close to the true value without causing too many high value bidders to reject their offers. But what we can ultimately show, though, is that this kind of approach leads to the best existing approximation guarantees that any auction offers for monotone submodular, general submodular, and even subadditive valuations. And what's interesting is the best known mechanism for additive valuations is also implementable in clock auction, implementable as a clock auction. So in fact, clock auctions are the state of the art, which leads us to a really interesting couple of questions here, right? The first question is just related to the mechanism design question here, right? How should one design a mechanism aiming to achieve a constant approximation for subadditive valuations? Clock auctions or otherwise, we don't know how to do better than a logarithmic approximation. The second question, which I think is broader and really fundamental, relates to the fact that for all we know, clock auctions may be as powerful as general auctions for this problem. And I think a real key question is in what settings is that actually the case? Can one pin down features of the mechanism design problem itself to identify whether or not clock auctions are as good as general sealed bid mechanisms? And when can they obtain close or comparable guarantees as general sealed bid mechanisms? But now I want to take a step back to more general questions as we conclude. The entire tutorial thus far, we've been thinking about binary single parameter auction settings. But there's a whole world of auction settings beyond this where there are many interesting open questions. Consider, for example, a single parameter non-binary setting that's really simple. We have a multi-unit auction where bidders have linear values in terms of the number of goods they receive. This is still single parameter since the private information of each bidder is just the slope of the line that they have for gaining more copies of the good. But this setting allows bidders to have multiple levels of service. It's not binary. This kind of setting requires completely revisiting the clock auction framework. And some initial work suggests that designing a clinching function, which describes not only what the current asking price is, but also what level of service each bidder has already secured and at what prices. But there are a number of non-binary single parameter settings for which there are no known clock auctions, let alone clock auctions that perform well. So I think a really fundamental question here is how should we be designing clock auctions in settings with multiple levels of service? But perhaps even more interesting is generalizing even further. More specifically, you can consider designing clock auctions for multi-parameter settings. As a really simple example, we can again consider a multi-unit auction, except where bidders have decreasing marginal utilities for receiving each subsequent good. In a sealed bid format, a bidder would then report each marginal gain for each number of goods, right? And for multi-parameter settings like this, even pinning down what a clock auction looks like is unclear. As we sort of have been discussing before, particularly sealed single price clock auctions are essentially just generalizations of posted price mechanisms. In a single parameter setting, the generalization is clean and straightforward. But in multi-parameter settings, we just don't know the right way to generalize posted price mechanisms. Do we use multiple clocks per bidder? Maybe perhaps again, we could consider a clinching function, and you may initially think to go try for this particular problem, for example, Ausubel's clinching auction, if you're familiar with that mechanism. But Ausubel's auction is notably not a clock auction and not even OSP. So while there are some very initial steps toward generalizing clock auctions to multi-parameter settings, I think the space is really almost completely wide open and the landscape completely unclear on how we should be designing clock auctions in settings with multiple parameters. So if you're like me and you agree that all of these great properties like unconditional winner privacy, obvious strategy proofness, and transparency are important, we really need a lot of new algorithmic tools to tackle settings beyond binary and beyond single parameter. And I'll just conclude by sort of showing for a couple of seconds a list of references that we talked about to varying degrees of depth in this work. And I'm happy to take any questions in the chat. Thanks so much.